Hi everyone, thank you so much for clicking onto the video. Today we're going to be looking at ligands and complex ions. So we're going to explain and use the term ligand in terms of coordinate bonding to a metal ion or metal, including bidentate ligands. And then we're going to use the terms complex ion and coordination number and examples of complexes with six-fold coordination with an octahedral shape and four-fold coordination with either a planar or tetrahedral shape. Then we're going to look at the types of stereoisomerism shown by complexes, including those associated with bidentate and multidentate ligands. So, for example, cis-trans isomerism in platinum NH32Cl2 and optical isomerism. We're then going to look at the use of cisplatin as an anti-cancer drug and its action by binding to DNA, preventing cell division. So firstly, we're going to introduce transition metals. So the definition of a transition element is an element that forms at least one stable ion with a part full d shell of electrons. Now, transition metal characteristics of elements scandium to copper arise from this incomplete d sublevel in atoms or ions. Zinc can only form a +2 ion, and in this ion of zinc 2+, it has a complete d orbital, and so does not meet any of the criteria of having an incomplete d orbital in one of its compounds, and so zinc is not a transition element. Now, the transition metal characteristics include complex formation of colored ions, variable oxidation state, and catalytic activity, and we're going to be going further in depth into all of these a bit later. But first we're going to look at some more definitions. So the first one is a ligand, and a ligand is a molecule or ion that forms a coordinate bond with a transition metal by donating a pair of electrons. So a coordinate bond is a type of covalent bond, but it's where one of the things donates both of the electrons. And the definition of complex is a central metal atom or ion which is surrounded by these ligands. And the definition of a coordination number is the number of coordinate bonds to the central metal atom or ion. Now we're going to talk about the different types of ligands that we have. So the first type is monodentate ligands, and examples of this are water, ammonia, and the chloride ion. And these can only form one coordinate bond per ligand. So for example, if we had chloride, it only has these two electrons which it can donate to something else. And so that's why it's a monodentate ligand, because it can only form one coordinate bond because it only has one lone pair of electrons. The second type is a bidentate ligand. An example of this would be the ethane dioate ion or the 1,2-diaminoethane. And these both have two atoms with lone pairs and can form two coordinate bonds per ligand. So if we see here the 1,2-diaminoethane example, we've got a pair here and a pair here. So that means that we can form two coordinate bonds with a ligand, and the same with the ethane dioate ion. And then the third type of ligand is a multidentate ligand. An example of this is EDTA, and this is the only one that you really need to know. And it can form 6 coordinate bonds per ligand. So the ones which bond are the ones on these oxygens with the negative charges, and also the nitrogens. And so on the right, we've got a diagram of how it forms coordinate bonds to the ligand, because it's 3D. So it can be quite hard to imagine how it kind of loops round. Now I'm going to talk about the shapes of complex ions. So the first shape that we get is an octahedral complex, and this is normally when we have 6 ligands. So transition metal ions commonly form these octahedral complexes with small ligands, so for example water and ammonia. And so as you can see, we've got copper 2+ in the middle and 6 ligands all placed equally spaced around this copper 2+, and that's how we get the octahedral complex. And then the second shape that we get is a tetrahedral complex, and this is when we have 4 ligands. So transition metal ions commonly form tetrahedral complexes with larger ligands. So for example, the chloride ion. So we've got cobalt 2+ in the middle and 4 chloride ions attached or coordinate bonded to it around the outside, all equally spaced apart. And so we have the overall charge of 2- because cobalt is 2+ ion and all the chloride ions are 1-, and we've got 4 of them. And then the third shape that we have is a square planar complex, and this is also when we have 4 ligands, but this only tends to happen with platinum and nickel metal ions. So here we have cisplatin, which is actually a drug for cancer treatment. So this is actually quite an important example that we'll probably look at later. And then the fourth shape that we get is a linear complex, and this is when we have 2 ligands. So silver metal ions tend to form these linear complexes. So here we have what we call Tollens reagent, and we test for aldehydes using this reagent, and we'll go through that a bit later on in the topic of testing for aldehydes and ketones. So octahedral and square planar complexes can both display geometric or cis-trans isomerism. And cis-trans isomerism is a special case of EZ isomerism, and they have this geometric isomerism with monodentate ligands and optical isomerism with bidentate ligands. So the first one we're going to look at is geometrical isomerism, and this is in octahedral and square planar complexes. So here we have an octahedral complex, and so we can see that the ligands which are different are these OHs that we have. And so here we call it cis because they are anywhere around the chromium but opposite. But the meaning of trans is that they are opposites. So they could be here and here, or they could be here and here, or here and here. But so anywhere where they are opposite to each other. So cis means anywhere but opposite, and trans means opposite. And this is the same for square planar complexes as well. And the second type of isomerism we're going to look at is optical isomerism, and this also occurs in octahedral complexes. So basically what optical isomerism is that the complex is mirrored. So on the left we have a complex drawn out, and then this dividing line is basically an imaginary mirror. And so the other complex, the optical isomer of it, will be like it's reflected in a mirror. Now we're going to talk about cisplatin. So cisplatin has a square planar structure, and this platinum 2 complex is used as an anti-cancer drug. The cisplatin works as 2 chloride ions are displaced and the molecule joins onto the DNA. And in doing this, it stops the replication of cancerous cells. However, it can also prevent the replication of healthy cells because it can't tell between cancer cells and healthy cells. And so by bonding onto these healthy cells and onto healthy DNA, it may lead to unwanted side effects like hair loss. One really important thing to know is that the trans isomer, transplatin, has no therapeutic effect. And so that means that we supply cisplatin as a single isomer and not in a mixture with the trans form. And that's because it would be less effective if we had the whole mixture in there. So on the left, this is cisplatin. And we can see that because these 2 chloride ligands are both on the same side, whereas for this transplatin, they are opposite. So this is a form of EZ isomerism or cis-trans isomerism. Now we're going to look at a quick question, which is to draw this complex. So first we look at the ligand. So we have this ligand, which is C2O4 2-, and we know this as a bidentate ligand. And so what that means is that it forms 2 coordinate bonds with the metal ion, which in this case is Fe3+. We know that because each of these ethane diarrhea ions is 2-, and we've got 3 of them, so that accounts for 6-, and so the Fe must be 3+ for the overall charge to be 3-. And so the molecule would look something like this. So we always start off drawing the metal ion first because it's easier. So we have Fe. And then now we think about it. So we've got 3 of these ethane dioates, but they're all bidentate. And that means that 6 coordinate bonds will be formed with this iron 3+. And that means that it'll be an octahedral shape. So we can start to form our octahedral structure. So we've got, I'll actually draw the bonds first and then the electrons. And then once you've drawn that, you then think about what bonds to what in this ethane diowate. So if I was to draw an ethane diowate out, it would look like this. So we'd have 2 carbons, 2 oxygens, and 2 other oxygens which are double bonded. And so we have some outer electrons here. And these are the electrons which form the coordinate bonds. And so we get something that looks like this. We have oxygen here and an oxygen here. And they are both bonded to carbons. And then we have these 2 which are double covalently bonded to the carbons. And then we have the same thing here. So we have 2 carbons and then another one. And so this is what our complex looks like. And then you have to remember to draw the brackets because it's an ion and then put in the charge. So this is the FeC2O4 3 complex. And so we know that in octahedral shapes, all the angles are 90 degrees. So we can say that the angle is 90 degrees. We can also talk about coordination number, and the coordination number is 6 because we've got 6 of these coordinate bonds on the Fe3+. So now we're going to look at another question, and it's to draw the 2 optical isomers of the octahedral complex CrOH2H2O4+. And so for the first one, we can just draw it however we like. So we start off with the chromium ion in the middle, and then because we've got 6 ligands all together and they're all monodentate, meaning they all bond coordinate bond to this chromium once, that means that we have 6 bonds to the chromium and it's got a coordination number of 6, and so we can confirm that it is an octahedral complex. So then we draw the bonds. And then now we attach the waters and the OH minuses. And for this first one, you don't really need to worry about where you put everything. So just dot it about randomly. And it's also important that the oxygen is what's next to the electrons because it's the oxygen which is donating the electrons. And so that's why you should always have the oxygens where the electrons are. And then we put in the bracket and then put in the charge. So now I've got my first optical isomer, and remember that optical isomers is basically what happens when you look in a mirror. So if we draw a mirror line, then what we need to do is we simply just reflect it. So again, we put in all the bonds. And then now we reflect it. So we've got H2O. So if we reflect it, then it looks like this. And then we have H2O here, and an OH here, and an OH here, and a H2O, and a H2O. And then we draw the brackets again and add the charge, and now you have your two optical isomers. Now we're going to look at a third question, which is to draw the cis and trans isomers of square planar complex PdCl2CN2. So they've already told us it's a square planar complex, so we don't need to work it out. So first what we do is we draw the central metal ion. So in this case we have palladium. And then we can draw the coordinate bonds. Then the next thing we do is draw the electrons, which have been donated by the ligands. And so first we're going to draw the cis isomer. So we're going to label this cis, and cis means together, so on the same side. So we're going to put two chlorines on the same side like this, and then two cyanides like this. And this is the cis isomer. And the trans isomer we have is if we draw all the bonds and electrons again. So trans means that they're on opposite sides. And so we put the chlorines on opposite sides to each other and the cyanides on opposite sides to each other. So we can have a chlorine here, a cyanide here, and a cyanide here. And this would be the trans isomer.